Okay, I think the
Great.
recording has
I
started.
think it's the recording is in progress now, right?
Mm-hmm.
Yeah, perfect. Great. Yeah, I think let's just wait for 1 or 2 minutes. In the meantime, I'll
Yeah,
introduce you,
yeah.
Matei. So yeah, we have here Matei Stan with us. He is a third year PhD student, and he has been working in state space models for quite some time. Today, we have got his presentation on the integration of SNNs and SSMs. It's a quite interesting blend of these two different research ideas. And I read the paper. It's phenomenal, really good insights from the paper. And yeah, I think we are all set to go. Mate, the floor is yours.
All
Uh,
right, thank you.
Take it away.
Yeah, so today's talk is about combining spiking neural networks and SSMs, state space models, which so I'll show they're a bit they're quite similar in computational primitives, but the uh, for most of the people that know neuromorphic computing, you probably know that one of the main goals of it is to um, improve on the tremendous energy consumption of state-of-the-art deep learning architectures. So, for example, when you have deep learning architectures like transformers and they've established state-of-the-art performance on sequence modeling, which includes language modeling, the most well-known example. We've seen over the past number of years their number of parameters explode from a couple billion to now reportedly, it's mostly rumors. I think I'm not sure if it's confirmed, but for the latest like GPT models, I think it's in the order of maybe trillions of parameters. So that has come at the cost of, an explosion in energy training GPT-4, which at this point already is a bit outdated. I think GPT 4.5 is out. Um, yeah, but that took to train that. It took the power equivalent of powering 700 homes a year just to train that one model. And that means that you can't deploy these models fully to like an edge device where you have energy constraints. And that also means that there's depending on the makeup of the energy grid, you also have a huge carbon footprint with this. So there's a real urgency to reducing this energy cost somehow. And luckily, we have some pretty miraculous devices in our or computers in our brain. Our brains are like they work off of like for me today, I'm working off of some bananas. So you can use a lot. It uses orders of magnitude less energy to perform really complex computations, and that are still not matched necessarily by state-of-the-art models. So there's a real merit to trying to imitate this efficiency from the braining to deep learning. And that strain of research has focused on building spiking neural networks, which are essentially relatives of recurrent neural networks, but they try to imitate the brain's efficient um, communication based on sparse trains of spikes. And the most common SNN backbone or model is called the leaky integrate and fire neuron, which consists of one component, which is linear integration, similar to an exponential moving average. And then you also have to generate spikes and communicate your output to the next layer of neurons. You also have a hard thresholding of this. The internal state of the neuron is referred to as the membrane and potential. And you threshold that. If it's above your certain threshold, it fires a spike. If not, it's silent. Um, and yeah, it's most of the time linear, and then you have this discrete nonlinearity that also resets your state. And these models are um, they shine brightest when you deploy them to neuromorphic hardware, where you can actually take advantage of the sparsity and you don't have to do dense matrix multiplications. Um, and yeah, they've definitely shown their potential. They have applicability in the real world. So they've when combined with hardware like Intel's Loihi, which is like a neuromorphic chip, um there were it's reported that yeah, you can consume up to 10,000 times less energy when you're doing a task like sequential MNIST, where it's essentially a sequence processing task where you feed in one pixel at a time from MNIST images. So you turn a grid into just a sequence of pixels. So yeah, classifying those on Loihi is a lot more energy efficient. So yeah, that's what you're striving for in our applications. And they've also been scaled up. This is already a bit old at this point, but there was this paper called Spike GPT, where they, on top of a linear transformer layer, they put a leaf neuron leaky integrate and fire, the model I showed earlier, on top of it to increase the sparsity of the communication between blocks in the network. And they managed to scale it to quite compared to normal SNN dimensions. They scaled it to hundreds of millions of parameters, which was an achievement. And But at the same time, it introduced some problems, which I'll get to later, that are somewhat inherent to spiking. But One of the biggest problems is that, like RNNs, SNNs require iterative simulation. So that means that you can't really take advantage of GPU parallelism when you're training them. And For example, when I was in undergrad and I was training SNNs for my final year project, it took me like days or even a week to train on sequential MNIST, which if you're just doing MNIST classification with an ANN, that takes you like hours or an hour or two. So it really makes training these networks really costly and not very practical. And that's one of the reasons why RNNs in general have fallen out of fashion compared to like transformers. And Another problem, yeah, with SNNs is that even though there's been efforts to scale them up, most of the literature still focuses on toy tasks. So actually quite short sequences. Even sequential MNIST, for the standard of some neuromorphic research that I've seen, some people claim that they're doing sequence modeling or long range dependencies with sequences of 200 tokens, which at this point is quite nothing for modern tasks. So yeah, there's a need to kind of bring spiking neural networks in line with the methods that you're using in deep networks. So compare them apples to apples. So for example, at the time I wrote the paper, one of the emerging um, ways to measure long range capabilities in deep networks was the long range arena, which included some somewhat NLP adjacent tasks where they were doing character level text classification or document retrieval to make the essentially make the tasks longer. Instead of having the words, you get characters, so you get to sequences of 2,000, 5,000 tokens. And then One of the most difficult ones that actually the transformer failed to do is something very similar to sequential MNIST, but much longer. If sequential MNIST is 28 pixels by 28 pixels, so 700 and something long sequence, when you flatten it, this pathfinder task where you have to you have a binary classification. You have to be able to tell if two dots are connected by one of these dotted paths, and yeah, doing that while flattening it. And the dimensions of these images are 128 by 128, so you get to like 16,000 tokens instead of 700 or 200, those scales. So you're really pushing to uh, uh, scenarios where you need a large memory capacity that's actually useful in real life. um, and That's compared, yeah, to the traditional neuromorphic tasks. like DVS 128, which is a bit shorter as well. Um, and yeah, the state of the art on the LRA was achieved after they discovered that the transformer can do this is the most extreme Pathfinder task is called PathX, the one that's 120 by 128. There's another smaller version, 32 by 32, which is similar to Cypher, but the thing that people were most interested in was actually converging on these very large tasks. And the first network to do that was S4, which is a structured state space model. um, yeah, in comparison to RNNs and SNNs, where they had that, you have the vanishing gradient problem, exploding gradients, and iterative computation. State space models are essentially just RNNs without any nonlinearity between time steps, which allows you to view the network. Yeah, you have an internal state again, as you had with the membrane voltage in the SNN, for example. So you can see the similarities with like the kind of leaky integration paradigm. But in this case, whereas in a traditional SNN, you have a one-dimensional membrane voltage for each neuron, here you're blowing up each state dimension so that you store information over multiple time scales. And when you have this when you have the so yeah you can see the we had the previous kind of plot of membrane voltage, like the leaky integration, the linear integration up to the firing threshold. Or in an SSM, you would have multiple membrane voltages, to speak, working on different timescales. Some decay slower, some decay faster. But yeah, the important part of having of removing the nonlinearity between time steps is that you can view the recurrence as a convolution. So you can do the whole operation in parallel with a fast Fourier transform. You multiply this kernel built with the recurrent matrix, and the B expands your input to the dimension of the hidden state, and then the C compresses it back to one dimension so you can apply a nonlinearity. Um, and yeah, there's obvious connections between these paradigm and SNNs, because yeah, you're doing linear integration, and then you could also apply a nonlinearity. And in the case of S4, those architectures, um, you're using GELU or a traditional, ReLU, traditional continuous nonlinearities, but you could just put a spiking activation there and see what it does. See if you can build spiking networks out of that. If you can still capture some of that so-called, magic of the initialization schemes they were using. Because yeah, a lot of the performance that you're getting in these networks comes from the way you're initializing the A matrix, the recurrent matrix. You have to have eigenvalues in that matrix that I think at this point they're just using diagonal matrices with complex eigenvalues with negative real part. And basically you want um, the eigenvalues to be contained in the unit circle so that they don't blow up, they don't explode, and they're close to the unit circle so that they don't vanish too quickly either. Um, but yeah, it's easy to do that with a linear network. You know what behavior you can expect. If you had nonlinearity in there, it becomes a bit more difficult. You might have to look at the Jacobians. There's papers looking into that, but it just makes your life pretty easy. So yeah, like I said, I saw these two architectures. They were very similar. I wanted to see if you can bring spiking networks into the modern age of deep learning by building them off of this new uh, SSM paradigm. And yeah, that's the paper I'll be talking about. Um, so yeah, just to reiterate what I've been going through. Um, you can see how SNNs are similar to RNNs, where if you unroll the computational graph, you have to pass through these nonlinearities at each time step. So you have to simulate everything sequentially. That's really slow. You can't do it that well on GPUs. SNNs, they do have the sparsity, but again, you still have to simulate it. And then yeah, you go to something like a transformer where you're just doing a massive matrix multiplication. It doesn't really have an interpretation um, in terms of dynamics like you would for an RNN. It's a bit more artificial. It's, you can see it as just as a linking all tokens together, but you wouldn't really be seeing a real neuron in the brain randomly remembering something with its attention matrix from some time steps ago and forgetting something in the middle. So it's kind of it's not very biologically plausible. So that's why transformers weren't really a platform for SNNs to go forward. It was philosophically antithetical to what they were doing, to what SNNs were doing. So that's why um, SSMs are exciting, because they retain the iterative deployment that you have in SNNs, in spiking networks, but then you can also apply them on GPUs. So you can use them on GPUs, so you can train them efficiently, quickly, and then deploy them efficiently like you would an SNN. Um, and yeah, the way I built it's pretty straightforward. What I did first, I introduced in a deep SSM. At each layer, you get at each time step, you get an input vector for each dimension. That this is for S4, but there's papers like S5 which combine this. But for the purposes of my paper, I just used S4, which has single input, single output. Um, SSMs that work on each channel of the input vector. Yeah, as I said, if you remember, the X state vector blows up the input, and then this is where the information is compressed. In the original S4 paper, the reasoning came from orthogonal polynomial projection theory and approximation theory, that you could compress the input signal history in a large, in a higher dimensional fixed width vector. Yeah, projecting onto a certain basis of your choosing. They've used, for example, Legendre polynomials, and yeah, others, depending on the kind of uh, memory uh, bias that you want. For example, you can have like a fixed width window of history that you want to compress, or you could have like an exponentially decaying memory that you want for the network. Depends on your application. But more recent studies have somewhat given up on the theoretical aspect of approximation theory and have just focused on spreading the eigenvalues of this recurrent matrix in a way that's expressive enough. And they've generalized basically the method. It's not rooted in orthogonal polynomials anymore. And yeah, when you compress back, when you want to output, like you do for a transformer, you have like a feed forward, a position wise feed forward network. And that's stacked at, yeah, each time step instead of between time steps. And to feed into that, you compress back your output with that C matrix, and then you pass it through a nonlinearity, and then through a matrix that does the feature mixing between these single input, single output SSM. So you're mixing the output from all SSMs and then passing on to the next layer. And that's where the binarization comes in between before you're doing the feature mixing, because that's where you would have a dense vector matrix operation. You, in general, for spiking networks, you want to avoid having multiply accumulate operations, and a way to do that is to just have accumulate operations, which are just additions, and you can do that if you have like ones or minus ones, where you have just subtraction or addition of the weights. You just add together the weights depending on what input there is to that feature mixing layer. So you avoid a lot of energy consumption with that. And yeah, that's basically the binary S4D model that I first looked at. And then I'll introduce another method. Um, so yeah, this is basically you get your uh, output from the SSMs, you make it spiking, and then you multiply it by um, a weight matrix for the feature mixing. But the problem here is that these spikes, and I'll get onto that a bit later, um, they are saturating. So one problem that's well known is that obviously they're non-differentiable because it's just a step function. So people usually just use surrogate gradients, um, something like replacing it with an arc, the derivative of an arctan, looking something like this, or a fast sigmoid in the backward pass. But another problem that still remains, even if you approximate it, you're going to have some accuracy degradation coming from the fact that yeah, you're approximating, you don't have the exact gradients. There's a mismatch between your error signal and what that network is actually doing. But then another problem that's I think maybe at the time I was writing this, I don't think it was as talked about, was that they're saturating activations no matter what. So spiking goes from 0 to 1, it's saturating outside of that range, which is the same problem that sigmoids or TANH has, and which has led to them not being used as often as compared to ReLU, because ReLU can let you just pass the you don't have any saturation, you can just multiply everything by 1 or 0, and in the backward pass, and yeah, you have it helps with non-vanishing gradients. You have a more stable signal in the backward pass. And yeah, I thought about this problem with spiking networks, and then I thought, okay, does um if your goal is to do energy efficient computation, so that means avoiding multiply accumulate operations, but you have this bottleneck of saturating activations, which is not something to do with what you're interested in with the um, it's something that you can't get away with spiking. It's inherently, it's kind of your upper bound. You're always going to be saturating. Then is there a way to get non-saturating gradients without having matrix multiplication, dense vector matrix multiplication with MAC operations? So the solution I came up with was to uh, have it's inspired by the gated linear unit. If you're familiar with that, it's basically passing your input vector at each time step when you're doing the feature mixing. You pass it through a normal linear layer, but then you gate it by a sigmoid applied to another linear layer. So it's basically two tracks going in parallel, and then you combine them with element-wise multiplication or addition, or in the case of glue is multiplication, and that allows you to have gradients that flow through the normal linear layer, but then you also have some nonlinearity in them from the sigmoid, so you get in practice it works quite well. It's quite widely adopted glue gated linear unit. So based on that, I worked on the gated spiking unit, where I took the that output from here that was passing to the feature mixing layer, the output from the different CISO, single input, single output SSMs. And first, there's an operation that's like the spiking ternarization, which is basically just having uh, um, -1, 0, or 1. So again, if you're mixing this ternarized uh, output from the SSMs with if you're multiplying by some weight matrix, again you're just doing additions or subtractions. So you still have that advantage from the spiking network. But this operation in turn is saturating, like the basic spiking function. So I combined it with a gate that passes the full output from the non-saturating output, like for an identity function, and then multiplied by ternary weights. So that means that you're again just doing addition or subtraction of the elements in X based on the uh, ternary values in the weights. Um, so you have gradients flowing to X through this gate, and then you have gradients flowing to the weights, the non saturating to, or if you were to apply a ternarization to weights, you know, it might be stuck to zero or something. But yeah, here you get gradients flowing in both entities basically, and then you like in the glue, you multiply them element wise at the end. I also played around with addition here as well, addition and maybe averaging or something like that if it's cheaper. And it degraded performance a little bit, but it still worked decently. But yeah, that's the main idea. You get, there's no bottleneck like before where your X was only accessible by a saturating bottleneck. Here it's accessible by two routes, and one of them is not saturating. So you should be getting good gradients backwards. And yeah, I tested this on long range arena to compare it to state of the art models at that time. And yeah, this is, I guess, a nice visualization of how much longer these tasks are compared to what traditional spiking network literature does. So sequential MNIST around 700, 784 tokens, elements, and then PathX, the long pathfinder task, 16,000. It's a different scale. And yeah, in this plot, the basic takeaway is that the red bar is the transformer, which performs quite poorly. And on PathX, the crucial one that it failed, it's 50%. So on a binary classification, that's random accuracy. It can't converge. The binary S4D, so the one with vanishing, with saturating activations, that's better than that. It's above 60%. So it's not quite the green bar is the just the baseline SSM that it's basically quantizing with that binary activation. Um, that's it's a lot lower than that on the PathX, the most difficult one, but it beats the transformer. It's above random. So that's claim to fame now for spiking networks. They can beat the transformer on this benchmark, or for long reasoning, for long sequence compression, basically. And then the gated spiking unit, the one where you don't have the saturating activation bottleneck, that's always you can see it, well, it's always within about 1% of the baseline accuracy, but it's quantized. It doesn't have those MAC operations in the feature mixing layer, which is the most it's the dense operation inside the you do get some MAC operations still in the inner workings of the SSM, but they are for what I was using the diagonal recurrent matrix, you only have like element wise operations, so that's cut down on operations a lot compared to a dense full matrix. um so that's one of the main results, that you can get binary or spiking networks based on SSMs beating the transformer on this long reasoning task. And another thing I looked at was yeah, sequential MNIST, just to compare it to some baseline spiking neural networks, and it beats those as well. And not to mention, I didn't list it here, but the time to train them is a lot shorter. For either of these ones, it's in the math, it's an hour or two. For these ones, it's a day or two. So it really speeds up training, and in this case, you get higher accuracy as well with fewer parameters in some instances. So that's quite a large advantage over both transformers in for long sequence compression, and also for compared to traditional SNNs. Um, and then this comes back to the story of how much is the saturating behavior of the binary spiking a problem for SNNs? And Here on this plot, I just took the if in surrogate gradient training, you have a surrogate function just in the backward pass. Here I just applied um, the same function in the forward pass as well. So basically, see if you didn't have any misalignment between the binary activation and the approximated gradient, if you had perfect gradients for a differentiable function, like the so actually applying that function as a nonlinearity, how much higher accuracy could you get? Could you just match the initial performance? And the answer is no. So you can still it you can the way I understood it is as if it's ceiling for what you can do with just spikes because they're saturating. Uh, Even if you had the perfect surrogate gradient, you still wouldn't be able to match the in this case the GSU, which is still it still has um, some approximations because it had you have to have the for those for the turnerization you still use some surrogate gradients. Um, but still, it seems like the problem is so these are you have some approximated gradients in here, but you also have non-vanishing, non-saturating gradients, and here you have perfect gradients, but it's saturating. So, and also there's for the binary one, there's quite a big impact with it still matters. So if you were able to get a better surrogate gradient, you could still improve performance potentially because here, when you're using fast sigmoid, which you can see once you get higher values for x, it decays more quickly, like the tails, and that's the problem. As the x input increases, you get further into this tail, and you get lower gradients, so more vanishing. Um, but so if you had better gradients, you could still improve it, but there's still a limit, and it's still far below what you can do with these non-saturating gradients. Yeah, that's the and also yeah this is a very rough estimate of how much energy you're saving. I'm not taking into consideration any sparsity induced by the turnerization or by spiking, and you still get approximately by cutting down on those MAC operations in the feature mixing layer, you still get it's still like half the energy of the baseline SSM, and it's within 1% of the accuracy on the benchmark in general, and then yeah, on the most difficult one, the path X, which the transformer failed to do, you're within zero point 0.8. So you get huge energy savings, and this is a very rough one. You could probably push this even further, but yeah, without sacrificing that much performance, which is something great for SNNs, where it's always been kind of a fact of life that you're losing performance even to LSTMs or networks that are no longer in use for language modeling. So SNNs were behind the last generation of networks, basically. Um, so yeah, the just to drive home the kind of conclusions from that, it's that yeah, you can still beat the transformer even with spikes. So spiking networks, based on SSMs, maybe there's an application for them if you don't want to use like the gated spiking unit, which for me it was mostly just a proof of concept to show that you can get, if you just have those non-saturating gradients, you can just push the network a lot further if your only goal is to avoid MAC operations. Of course, you're breaking biological plausibility, but um, at the same time, on Loihi, on the neuromorphic chip I mentioned earlier, Loihi 2 has graded spikes, which are basically, I think, integers. Uh, so you can get, you can't really do that in real neurons. You don't have integers. You still have spikes. So there's a rift forming between neuromorphic computing that focuses on performance, and then neuromorphic in the sense of keeping it brain inspired. And I think I've been seeing that a bit in the literature as well. There's been some and I'll get to some examples as well. Um, there's a disconnect between, yeah, these are like, there's been a research area that has focused on quantization of SSMs, which has somewhat taken over the performance oriented neuromorphic computing community. So you're looking at, yeah, for example, the Matmul free transformer, basically a linear transformer which looks very similar to an SSM, but it has a different initialization with ternary weights in the feature mixing. That's basically Matmul free, from what I understand. And then you also have work on quantizing these networks. There's been more work since quantized S5. But yeah, you have this performance oriented neuromorphic community now that's more going towards quantization. And then you also have the brain inspired, more theoretical neuroscience community that keeps SNNs to a small scale. They introduce, which is not to, it doesn't mean that it's not valuable for computing as well, because they've been looking at, for example, I think neuromodulation in SNNs, which similar to newer selective state space models like Mamba. So there's still a value in trying to bring biological realism for the kind of the long-term goals of neuromorphic computing, learning algorithms as well. That's a big part of researching brain-inspired methods. Um, but yeah, there's been this shift, and I think at the time I worked on my paper, it was just kind of coming together, uh, this shift. And yeah, that what I mentioned about selective state space models, that maybe there's still something neuromorphic about them as well. And SSMs have, I think they've had their moment in the limelight last year, perhaps in large language models. I think I've talked to some people in working with pre-trained models who kind of saw state space models as a fad for 2023 or 2024. They were really excited about Mamba, but then there are some results that show that for language modeling, it's still not quite as good as transformers. So when you only care about raw performance and you can throw as many GPUs as you want at it, then maybe there's not, you don't get as excited about them. I've heard that, yeah, people at Meta, I think they were considering Mamba as being a bit of a fad that went away. But for neuromorphic computing, I think they still represent the closest thing to taking SNNs forward, to have them compete with modern architectures. And if you're thinking about efficiency, then you still have an advantage for state space models over transformers. You go from quadratic complexity for attention to n log n for state space models. So linear uh, um, complexity. So I think there's still a future to be excited about for state space models, especially in neuromorphic computing. And maybe once people understand them better, as there's a lot of theoretical work going on at the moment with state space models and parallel architectures in general. There's this topic of state tracking, where you want to do tasks like regular languages, where you have to keep the simplest example is to keep track of whether a sequence of parentheses is correctly closed. If you have a number of parentheses, it's kind of like you would implement it in a stack or something like that. It's a really simple task, and RNNs can get 100% on that. But transformers and state space models can't really do it with a single layer. There's papers that show it, that you have to scale the number of layers with the number of inputs in the sequence. So that's not really that great. So maybe nonlinear RNNs could make a comeback as well in that regard. And we've seen also for reasoning, there's a sort of recurrence in there as well when you apply the whole layer uh, recurrently, if you're refining basically your representation. So there's multiple research areas that have sprung up since then. So yeah, just seeing where you can take the SSMs, where both SSMs and transformers fail, and maybe if we get better training algorithms than backpropagation, where you wouldn't have to uh, have a lot of epochs to train the network, then maybe simulating it in sequentially won't be a problem anymore that much. Um, so yeah, that's I think the state of SSMs at the moment. So yeah, I think that's about it for the talk for this part.
Thank you, Matei. Uh, Great presentation. You have nicely distilled the most important concepts from your paper, and then you have presented them or aligned them in a very easy manner for us to understand. Great. So I think we can stop the recording of this
Mm-hmm.
presentation, and then we can head to our discussion. I have a bunch of questions. I'm pretty sure our other